Layout Nuggets, precision insights for smarter designs. Current nets or voltage nets? What's the difference between a current net and a voltage net in analog layout? Let's break it down. Nice and simple. Current nets are designed to carry current, whether it's constant or mirrored, like in bias chains or current mirrors. Voltage nets, on the other hand, are all about holding a fixed voltage level. You'll find them on reference nodes, op-amp inputs, or control lines. Two very different electrical behaviors. And trust me, they need very different layout strategies. So next time you route, ask yourself, is this net carrying current or holding voltage? Which is more important to protect in layout, current nets or voltage nets? Well, the answer isn't that simple, because both are critical, just for different reasons. Current nets demand low resistance paths to ensure accurate current flow without drops or detours. Voltage nets, on the other hand, need shielding and isolation to avoid noise coupling and prevent voltage drift. So really, it's not about which one's more important, it's about what risk you're trying to avoid and how you protect against it in your layout. Let me give you a few examples of current nets that need protection, especially in analog modules. Think of bandgap reference chains, bias current mirrors, tail currents in differential pairs. These nets aren't just wires. They carry precise currents, critical to circuit behavior. And if there's resistance or worse, asymmetry, it doesn't just disturb balance, it directly impacts performance. So yes, current nets need just as much care, but for very different reasons. What about voltage nets? Which ones do you really need to protect? Well, think about VREF lines, VCO tuning lines, a DC reference inputs. These nodes are sensitive, very sensitive. They can easily pick up digital noise, substrate coupling, or crosstalk, and that leads to erratic, unpredictable behavior. So remember, these aren't just lines on a layout. They're the anchors of analog precision, and they demand layout discipline. What layout techniques do we use to handle current nets? Let's break it down. Wider metal traces to keep resistance low. Multiple vias to reduce via resistance and improve reliability. Symmetry in routing, especially in match current paths. And yes, avoid unnecessary jogs. Keep it clean and direct. Because remember, resistance kills precision. And EM violations, they're not just warnings. They're a real threat to performance. So, lay out current nets with care and with respect for the current they carry. How does electromigration affect current nets versus voltage nets? Let's start with current nets. Electromigration, or EM, is a big concern here. Why? Because it's current density that causes metal to wear out over time, leading to failures you definitely don't want. But when it comes to voltage nets, they typically carry very little current, so EM isn't the main worry. The real threat? Noise coupling, substrate injection, and voltage drift. So remember, as for current nets, it's EM. For voltage nets, it's noise. Two nets, two very different risks. How do you deal with noise-prone voltage nets in layout? Simple. You shield them. Use ground shielding. It's your first line of defense. Keep them far away from aggressive digital lines or high-speed signals. And yes, don't hesitate to use extra spacing, guard rings, or even dedicated metal layers if the design demands it. Because in analog layout, protecting your voltage nets is protecting your precision. What about differential circuits? How do nets behave there? Well, in differential design, symmetry is king. Both current and voltage nets must be laid out in a way that's matched and perfectly balanced, because any mismatch, even a small one, can impact CMRR, offset, and yes, even your gain. So remember, in differential layouts, symmetry isn't just nice to have. It's non-negotiable. How do you isolate sensitive analog voltage nets from noisy digital current paths? The simple answer? Physical separation, use guard rings, use deep N-wells, use dedicated power domains, and metal shields. The goal? To trap the noise and contain it before it spreads. Because in mixed signal layout, isolation isn't optional. It's what? So here's your layout nugget from Semionics. Every net tells a story, current or voltage, and layout decides the ending. Design with intent, route with awareness, and deliver with confidence. For more such high-impact learning, visit academy.semionics.com, because at Semionics, your VLSI journey is just a click away. Happy learning, and see you in the next one.